Run kubectl describe pod name immediately. The events section reveals the scheduler's decision failure. A pending status confirms the pod definition is syntactically valid, but the scheduler found no suitable node for placement. The scheduler operates in two phases: predicates and priorities. Predicates are hard requirements. Failure here is the root cause of pending. We analyze the output for failed scheduling messages, specifically looking for insufficient memory or insufficient CPU messages within the event log. If the scheduler cannot satisfy all predicates, the pod remains unscheduled, regardless of priority scores. This initial command provides the exact reason code needed to proceed with targeted debugging. Node capacity is the primary bottleneck for pending pods. Check the pod specification for resource requests defined under containers.resources.requests. These values dictate the minimum resources the scheduler must reserve. Compare these requested values against the available allocatable resources on all nodes using kubectl describe node. If a node has 4 GB allocatable memory and your pod requests 5, the node resources fit predicate fails instantly. Requests are reserved capacity, not current usage. High utilization does not cause pending, but insufficient reservation capacity prevents scheduling. Ensure the sum of all requested resources on a node, including the new pod, does not exceed the node's allocatable capacity. Namespace-level constraints often silently block pod placement before the scheduler even considers node capacity. Execute kubectl describe ResourceQuota in the target namespace. Verify if the pod's requested CPU or memory exceeds the quota hard limit defined for the namespace. If the pod definition omits requests, limit range objects might inject default values that subsequently violate the resource quota. Use kubectl get limit range-o YAML to inspect these defaults and calculate the effective resource request. A common error is exceeding the quota count for persistent volume claims or services, even if compute resources appear sufficient. Quota violations are reported directly in the pod events as failed scheduling due to resource quota. If the pod mounts a persistent volume claim, the pod remains pending until the PVC is successfully bound. Run kubectl get PVC name to check the status. If the status is pending, the scheduler cannot proceed with pod placement. This usually indicates the absence of a matching storage class or insufficient available persistent volumes if using static provisioning. Check the PVC events using kubectl describe PVC. Common causes include misconfigured volume binding modes, such as wait for first consumer, which requires the pod to be scheduled first, creating a circular diplodency if other constraints exist. Ensure the provisioner is running and communicating correctly with the underlying storage system. Explicit placement rules override general scheduling logic. Inspect the pod specification for node selector fields. If the specified label key value pair does not exist on any node, the pod stays pending indefinitely. For complex scenarios, examine NodeAffinity rules. Required during scheduling, ignored during execution rules must be satisfied immediately for scheduling to proceed. A typo in a label value or key is a frequent cause of NodeAffinity failure. Use kubectl get nodes-show labels to confirm label presence and accuracy across the cluster. Remember that anti-affinity rules can also prevent scheduling if they mandate separation from existing pods, leaving no valid placement options.
Taints prevent pods from being scheduled onto a node unless the pod explicitly tolerates that taint. Use kubectl describe node name to view active taints. If a node is tainted with no schedule, only pods possessing a matching toleration key, value, and effect can be placed there. Ensure the toleration block in the pod specification exactly matches the taint definition. Taints are often applied automatically by the control plane for maintenance or resource pressure, such as node.kubernetes.io/disk pressure. If all available nodes are tainted and the pod lacks the necessary toleration, the pod will remain pending, failing the taint toleration predicate check during scheduling. Pod priority determines the order of scheduling attempts. If the cluster is resource constrained, lower priority pods may wait behind higher priority ones, even if they are technically schedulable. Check the pod specification for the priority class name field. If the scheduler cannot find resources, it attempts preemption, evicting lower priority pods to make space for the current pod. If preemption is possible, the pod status might show a nominated node, indicating where it intends to land after eviction completes. If no preemption target exists, or if the pod is the lowest priority, it remains pending, waiting for resources to be released naturally. The kubectl describe output is the single most critical debugging tool. Focus intensely on the events section at the bottom. Look specifically for the reason field being failed scheduling. The message field provides the precise predicate failure count, listing exactly which nodes failed and why. For example, the message might state, 3 nodes failed due to insufficient CPU, 2 nodes failed due to taints. This numerical breakdown immediately isolates the problem type, directing you to resource adjustments, toleration fixes, or node label corrections. Always read the full message. It often contains the exact node names that failed the check, allowing for immediate node inspection. DaemonSets ensure one pod runs on every matching node. If a DaemonSet pod is pending, it usually means the node it targets is unschedulable due to taints, or the node is marked as ready but has 0 allocatable resources. DaemonSets ignore the standard scheduler and rely on the DaemonSet controller to create pods directly on target nodes. Static pods, managed directly by the kubelet configuration file, bypass the scheduler entirely. If a static pod is pending, the kubelet failed to create it locally, often due to local resource conflicts or invalid manifest syntax in the kubelet configuration directory. Check the kubelet service logs directly on the affected node for creation errors. When standard events are inconclusive, inspect the Kube-scheduler logs directly. Enable verbose logging level 4 or 5 on the scheduler component to see detailed predicate evaluation results for every attempted pod placement. This reveals exactly which node failed which predicate check in real time, providing granular insight into the decision process. For persistent issues, consider using the scheduling framework extension points to trace custom plugins if your cluster uses them. Remember that the scheduler cache might occasionally become stale. Restarting the scheduler deployment forces a cache refresh, resolving rare synchronization issues between the scheduler and the kubelet state. This is the final step when all other checks fail.